Hi everyone, my name is Paulinetta and I'm very glad that you came to hear my talk about compiling pattern matching to in-place modifications. This is a joint work with Laura Gonor and Gabriel Radan, and before diving in, I just want to precise that except for the very first slide, data structures will always be stored in arrays. That is no pointers manipulation at all, and it will all about memory movements. So here we are. We noticed that when we need to write a transformation on a data structure, we can either use a low-level data language like C and have control over performance and how copies are done. But if we use high-level languages, we have a domain-specific language to manipulate types with pattern matching. However, we can tune or modify how the type is stored in memory, nor control how copies are done, but we don't have to fiddle with memory, which is great. So our goal is how to take the best of both worlds, that is, keep the very convenient approach provided by high-level languages, but still provide ways to control the memory layout and enable in-place structural modification. All along this talk, we'll try to address this transformation where a subtree A is pulled up, that is, a rewrite of the former tree by its right subtree. First and foremost, it's important to remind that the tree is stored in an array. At this point of the talk, how the tree is laid out in memory is of no importance. So here is our domain-specific language to describe in-place structural modifications. That is, a collection of rewrite rules containing a data structures. Here we are matching the whole tree, and we are putting the focus on its right subtree, which will overwrite everything. Now we will see how we describe internal memory movements. A is not in the final tree, so we can discard it. Same goes for I. We discard it. B can be moved easily, and the same goes for J, but we can do the same for C, because even though we can move the left child of C over B and J with the rest of C conflicts with itself. In our rules we can detect it because the destination and the source share a common prefix. In order to do that, we cut the tree into independent layers. If we suppose that the elements of the tree are stored in the order they are visited by a breadth-first search, we can display the tree this way. The 0th layer has 1 element, the first has 2, the next has 4, and so on. Now let's see. I'll be fast on this slide because nothing changed much. The only thing is that we now move all the layers of a subtree. That's the notation VK, which means try to move as many layers as you can. And we use different K because the value we can take depends on the number of layers of a subtree. As before, we can get rid of A and those of all its layers. We can move I, B and all its layers, and same for J. So let's see how we do for C. We can unroll C. When we unroll C, the following roughly appear. First, we map up the constructor node one level up. That's why you can see in the rule that k2 plus 2 becomes k2 plus 1. Next, we do the same for the integer. And now we can move the subtrees along the rough way. Thanks to those rules, we can now map all the places we have to move and we can plot them in a coordinate system, which is the case as axis. The layers of B are moved as we move over the axis K1. The integers are moved along the axis K2. And C has been split in many layers movement, which can be shown as this triangle. We can also map out the dependencies. B in blue can be moved freely, and the other ones makes the dependency between layers appear, and here we can see each layer on one line, and there is a dependency in between those layers. Those dependencies can be expressed as linear relations over the k variables and given to an integer linear program solver, which produces a scheduling which respects the dependencies. Here we schedule. The scheduling gives us the following, where points have to be executed with respect to the lexicographic order. After that, to produce the code, we use Quillray's algorithm, which can scan polyhedra and produce the loops you can see on the right. Yeah, the presentation was pretty dense, and I encourage you to see our paper for more details. But to sum up, we have a promising technique to compile structural transformations expressed as pattern matching rules. These techniques use many different tools, like time rewriting, regexp, from which we can extract linear equations that are used to produce a polyhedric schedule from which we can then generate code. In the future, we would like to extend the input language to support recursion and guards in order to be able to perform computations on the values in the nodes as we move them. And now that sequential code generation works, we would like to produce parallel code by applying some information from the schedule that we have harnessed. We haven't harnessed yet. Thank you very much for your attention.